So hi everyone, this is me, I'm Gabriele. I'm a software developer. I do a few things in my life. I work a day at Buildo, it's a consulting company in Italy, in Milano. And by night, I do a couple of things for the community, which is organizing the Milano Scala group in Milano, the user group of Scala, and the Scala Italy conference, which moves around. This year was in Rome, last year was in Venice, next year is going to be in Florence. So if you want to have an excuse to come to Italy and take a little vacation, that's your perfect excuse. So to the main reason of this talk, I'd like to provide some context first, like what is this talk and why am I doing it? So you've seen this morning, who was at Harry's talk this morning about stacks, monostacks? Okay, so that talk was about solving the monostacks problem with different techniques. So today, obviously, I'm focusing on monotransformers, but what I would like to provide is some context on which problem exactly we're solving. And then we'll see the monotransformers are just one solution, and there are many other. And the reason I'm doing this talk today is that when I started learning these things, there weren't much resources, and I wished I attended a talk that explained me a few caveats that you're facing, and especially explaining the problem. So I want to do this talk, and I want to do it now because I still remember the pain I went through, and I think I can provide some valuable insights to you guys. So, as every good story, we start from a question. It's not a very important, very heavy question. It's just a Stack Overflow question. And it's about essentially this. So our problem is mapping 2 times. This is the incredible problem that was nagging this user on Stack Overflow. So the idea here in the core of the problem is like, OK, I'm doing map on a future of a list. And then I'm doing map again because I'm accessing the future and then mapping on the list. Like, sounds really silly at its core, this problem. So, and the question was, can I do any better? Is there any Scala trick that I can use to improve this code? So one reasonable answer that was posted already, it was indented. And I think that was pretty reasonable. I actually upvoted the answer. And it's probably the most reasonable answer in this case. But I love getting Stack Overflow points. So I decided to apply some science and get some upvotes on Stack Overflow. So whenever we say in science, in the context of functional programming, usually we refer to category theory, which is a very helpful branch of mathematics from which we can derive some interesting concepts that are helpful in computer science. So functor is what we're talking about here. So functor, for us today, is just an interface. It's usually referred to as a type class or a category, but in this case, it's just a trait. It's a trait that has a type parameter, which is this f, which in turn has another type parameter, and it just defines a map operation. So whenever you have a map operation on a type, you could technically be implementing a functor. This is almost true. So for instance, whenever you see a future and a map, technically you could define it like this. So you could define a functor for your future that here conveniently just uses the map function on the standard library. But you can rephrase it, let's say like this. So you can see future having a map operation as the fact the future has a functor instance. Okay? So whenever we do something like future map or list map, you can think of them having a functor of a future or functor of a list, and then applying that operation that is defined on the functor. Okay? So an interesting thing that comes from category theory is that functor is a structure that composes. So if you have 2 functors, so you know how to map on 2 things, like a list and a future. If you want to know how to map on the composition of the 2 things, like a future of a list, or a list of a future for the matter, you can just compose the 2 functors together, and you get this super functor that can map over the combined structure. So what we're doing is essentially this. We're just merging the 2 things, right? And now, for free, out of nothing other than knowing how to map on one and the other, if you combine the 2 things and you have a future of a list, you can combine the functor, and then you can operate directly on this data structure. So what we're doing here, in practice, using actual Scala code that works, you can copy-paste this, provided that you have cat in your dependencies. The really interesting bit here is this. So we're doing composition, literally, like future, functor of future, compose functor of list, and then we're using that thing that has a map operation to map over this data, which is a future of a list, which solves the original problem. So you get a lot of points on Stack Overflow, which is amazing. So we have a single map and a single function. And well, a quick parenthesis, I'm using cats for this talk. If you used to Scala Z or other function libraries in Scala, feel free to use them. They're essentially verbatim the same, the examples. Probably there's some minor syntactic difference, but it doesn't really matter. The concepts apply to any library that provides these tools. So CAT is a library, again, that provides some category theory-based tools for functional programming in Scala. So we've seen an example of mapping, and it was wonderful that we can just do one map instead of two, because we composed the function before applying it. But that mapping is the easy one, right? I mean, sometimes we map, and it's wonderful. We do these very interesting things, like adding one to a number in a list. But sometimes, from the map, we return another list, right? And that gives us a list of lists. And oftentimes, it's not what we want. Possibly list is the only case where that may make sense. If you're being particularly lousy on types, list of lists may mean something in your domain. But usually, other types don't, like option of option. Doesn't really mean much, right? It's not super optional, and what is definitely there or definitely not there, I don't know. Future is not super asynchronous. It usually doesn't make sense to stack those types, right? So we want to squash them together, and most of these types has these flatten or other names operation that just takes x of an x of a y and then just squashes them together into an x of a y. So a list of lists, you get a list. Future of futures, you get a future, and stuff like that. So this is so common that you map over something, you return the nested data structure, and then you flatten it together. Then, well, without much creativity, we have an operation that combines the two, which is flat map, which is the combination of flatten and map. So you map over something that you flatten, you have a flat map. You can do it in a single pass. So you have these operations which are essentially the same. So you're mapping it, and then you're flattening. Is slightly more efficient to do it with a flat map, but the semantic is the same. So this is great, and in general, this is kind of a rule of thumb. If you end up with a future, you probably forget a flat map at some point. This is a very stupid rule of thumb, but it usually applies. So for instance, you have a future that you map over it, you return another future. Oh, wait, you need to flat map, right? That happened to everybody. So I draw a correspondence between map and functor, saying the map is the operation defined by functor, which is a type class. I'm going to do the same thing with flat map, and you all know what I'm talking about probably, which is the monad type class. And the monad type class is this carry word that gets used a lot in functional programming, and the reason is that it's particularly useful. And monad is characterized by a few operations, but a very interesting one is flat map, and it's actually a part of flat map, which is the flat part. The flat part is what defines what a monad does, essentially, and it defines what it means to squash things together. So the fact that you can flatten types usually can be interpreted as these types having an instance of a monad. So what does it mean to flatten two futures? I don't know, but if you have a monad instance for that specific type, you can say. And flat map is the concatenation of mapping, is the composition of mapping and flattening, or joining in other terms, which is the interesting bit of a monad. And since you can derive a map starting from a flat map, it's just a generalization of a map, a flat map, you can actually say that every monad is also a functor. So in case you have a monad instance, you can also do all the operations that a functor provides and some others. So again, this is the interesting bit. Let's see another example. So this is slightly less contrived. We're starting to get to like a real world code. So we have two functions, get user and get address, and they both return their value wrapped in a future, okay, because it's asynchronous. So if we want to compose them together, we know the trick, and we just do flat map once, and then we just do map, and we retrieve whatever we're interested in. In this case, is the city. So this pattern of concatenating things, in this case futures, but could be anything that has a flat map operation, is so common that we have a special syntax for that, which is the for comprehension. So if when you were learning Scala, you were told the for is like a glorified for loop in Scala for doing loops, this is not actually true. This is very different. And if you've been programming with Scala for a while, you realize it by now. But sometimes we tell this lie that it's just a for. You don't have while, you have for in Scala. It's not actually the same. You can use it for looping, but that's just part of the story. So this is verbatim translated to essentially this. There's a step in the compiler. Mirko was talking about steps in the compiler before. One of the 24 steps actually does this transformation from the for comprehension to the flat map concatenations. So we have this nice syntax, and I would argue that this is what we always aim for if we're writing business logic, right? This is clear. It's clear what we're doing. It's sequential. Is sort of an imperative style, which is convenient to read when you're reading an algorithm or a business logic piece. Like, do this, do that, and then extract this value. So for all the talk, this is what we're aiming to. We're aiming to writing code that looks like this, which is easy to read, that has as less cognitive overload as possible while trying to understand what a code does at a higher level. So some lessons that we learned so far. So monads and its flat map operation allows for sequential execution. So you can chain things together. As it's not combination, that sometimes the flat map operation is also called bind because you're binding things together, or chain because you're chaining things together. So monads can squash an f of A into an f of A. So they have this power of joining things together. Any questions so far? This was like groundwork for the talk. Okay? So, wait a second, we just talked about f of A, right? But this is not really interesting. In real life, we always face these cases, f of g of something. What do I mean? So let's go back to the example, and we realize something that is really not okay. We're getting a user by its name, by fetching it, I don't know, from the database, and it's an asynchronous operation, which is wonderful, and if the feature fails, usually that conveys the meaning that something has gone wrong on the connection, on the database transition, or something like that. But if the user is not there, because we don't have a user with that name, usually we want to provide an extra level of semantic and just handle the case differently. And usually it's done like this. You use option. So you have a future of an option, which represents two very different things. The operation is asynchronous, and it may not yield a value. It may just return nothing, which is a reasonable case that we want to handle. It's not something unexpected. So we do this, and we go back to our example, and we realize something. CD now would be a future of an option of a string, because definitely the CD could not be there, and it's an asynchronous operation. But then this doesn't compile. Is it obvious why it doesn't compile? Can anyone say? The first type does not match the second type. Name values. So, right. So, exactly. So here, what we're getting is when you do the back arrow, you're essentially doing a flat map. You're binding a value into a scope. So Gab now has the value of whatever the flat map binds it to, and in this case, is an option of a user. And then you're trying to pass it to a function that expects a user. So that wouldn't work. Okay. So in case it's Friday, and in case you're hungover, you do something like this, right? And you just ship the code and everything works. Amazing. Don't ever do this. So don't. The emoji tells you not to do it. So, but this is like frustrating, right? You get to this and you're like, fuck. Can I swear? Okay. So you eventually do something like this, which is sad, because now you're talking about cognitive overload. This is all boilerplate, essentially. It's like, okay, just do this contortionist thing to get the value out and just do a match inside of from comprehensions. You can sugarcoat these as much as you want, but it's going to be awful, especially if you have many of this, not just two trivial values like I've done here. So what you need to do here is to match on the user, which is now an option, and then do different things. And in the none case, you're doing something that you didn't even think about, which is returning future successful or none, because it's a successful future or not. You're actually handcrafting a value that you didn't really care about. It's just there to fill a gap, right? It doesn't add any value to, say, future successful or none. It's really just frustrating. What you would like to do is something like this, like double back arrow, like extract 2 times. And that'd be great. Like, we want to go deeper. We want to access the value inside the future and then access the other one. Can we do that? Is that a syntactic problem that Scala has that doesn't allow us to do that? Yeah, that'd be great, right? Like, recursively. So, thinking about a lesson that we learned before, maybe we can say, okay, we have a monad of a future, we have a monad of an option. How about we squash the two, right? So we have a super flat map operation that can work on the combined type. So future of option gets its flat map out of thin air because we know the two things. So this, right? And nope, sorry, that cannot be done. And that's why we're here talking about this thing. And combining two monads together, like we've done with Functor, it's just not possible. It's not impractical, it's theoretically impossible. And if you're curious about the details of why and you want to try yourself, there's this blog post by Tony Morris that explains that in very few complicated lines of Scala. And so what the blog post does is go through, okay, try to implement the compose operation on Functor. Easy peasy, one line of code. Try to do the same with applicative, which is another type class, which is slightly more powerful than Functor, but less than monad. Okay, some few lines of code, some weird symbols, but we're getting there. Try to do it with monad, and you realize when you try it, it's like, oh, okay, no, I cannot do that. It's impossible to do it, and it's very clear once you try. So I encourage you to try to do that, and to fail, because that's how you get why this is impossible. But for now, just bear with me, it's impossible. So what is the impossible part? Essentially, we would like to write these two functions. The first function is trivial. It's literally one line of code. I could have put it there instead of putting an emoji there. The second one is impossible. And the impossible part is that you cannot just compose two monads together and have a third monad, which is a combination of the two, just by the virtue of the fact that the two things are monads. It's not enough information to do this operation. With Functor, it is, because Functor is very simple as a structure, and having two things that are functors is enough to get a third functor. I just need to know that they are functors. I don't need to know about futures, I don't need to know about list, and I don't need to know about option. With monad, that's impossible. So generically, you cannot compose them, but if you pay attention, you essentially already specifically compose them, right? You're working with that. That code compiled and worked. So you were composing two things and working with the composition of the two things. So you must have done something right? So if you pay attention to the example that we've seen before, we have essentially written a flat map that works on future of option. We just handwritten it. We didn't magically compose it out of parts. We just handcrafted it. And this is exactly what we can use to encode this flat map for future of option, specifically for future of option. So going back to the monad interface, essentially what we need to do is to implement this interface, this trait monad, for a data type which represent those two types together, like future of option. So in order to get it done, what we can do is to just wrap a future of option inside a class, and then implement a flat map for that class. So whenever we need to flat map over a future of option, we just wrap it, do the flat map, and then unwrap it, which is fairly easy. It's like defining a new type that we can work on. So we do something like this. We have a case class for convenience, which is fut_opt of A, and it just wraps a future of option. And now we go defining a flat map operation and a few others that are map and pure for this data type, which can be useful. So I'm not going through this because it's really simple. I could do it, and it's essentially the same code as before, so anybody can do it. It's just essentially saying, okay, that piece of code that I hadn't written in my for comprehension, I'm going to call it flat map and extract it and put it in a trait. That's it. The rest is trivial. The map is just map and map, which is the original example, and the pure is just, okay, wrap an option, wrap a future, and you're done. Okay, so let's use it. And it's really, really simple. This is starting to get back to what we started from, right? This is, again, less boilerplate than before, and it's readable. So we just wrap future of option, and now what we get is a future of option, because we flat mapping over that. And then whenever we need to get a future of option back, it's just dot value, because we just need to extract it from the case class, and we're done. So this is quite cool if you have exactly future of option, right? But if you have something like list of options, because you're returning a list of users or something, why, let's do that again, right? So we have list of option now. We wrap a list of option, and we do the same thing. And we're starting to notice a pattern, unless we're very insane. So this is list of opt, the monad for list of opt. This is the monad for future of opt. Notice some similarities, okay? So the only part, let's try to see this, okay? What changes? Is literally changing the name and a few other things, right? And especially the interesting part is still this one. It's still the knowledge that we need to have about option. And if you take a look at this code, you don't see anything specific about list or about future. You just do calling regular monad operations on list and future. Like, you don't even need to know what those types are. Take the future, the pure, for instance. You're just calling pure of option and pure of future, which doesn't give you, it doesn't require any knowledge of future specifically. What is future? I don't care. It just needs to have a pure operation for me to work with that. Same thing with a map. And actually, same thing with a flat map if you consider the future. When you do fa.value.flatmap over here, you're just using the fact that this value is of type future and has a flat map. So you're not doing anything specific with the future. So you can abstract it out. Instead, with option, you need to essentially do a pattern match. You need to know how an option is made in order to work with it. So option is the interesting part here. So we can do a more generic approach and do this whatever option, and W stands for whatever. And now we have another type parameter that represents whatever thing is around this option, right? Whatever thing is composing with this option or is transforming this option. And now W can be any monad. Anything is fine. I mean, I didn't constrain the monad here. You can do it on a single level operation, but you just need to ensure that this W has a pure, has a map, and has a flat map. So has a monad instance. So I'm not going to go implement that because it's becoming trivial, and you guys are a smart audience, so you understood where I'm going. So we'll meet option T, which is whatever opt from the slide before. So option T is a data type that exists, and we just accidentally invented a monad transformer. So option T is the first monad transformer that we see today, and is this type, which looks a lot like option. It just has an extra type parameter and has a T in the end. And F can be any monad. So this is essentially a flattened representation of F of option of A. It just flattened out with 2 parameters instead of a nested structure with 1 parameter. So with option T, we can do the same thing as before, but now it's more generic because we don't need, whatever thing has an option, we wrap something around it with another thing that is trying to compose with this option. If that thing is a monad, we can just use option T and we're done. We don't need list of option T. We don't need future of option T specifically. We can just use this option T that is already provided by libraries like Scala Z and cats. So this is nice, and in general, this is the pattern, right? If you see other transformers, you can easily grasp how they're going to be transformed to. You have foo of bar of something, that you end up with bar of T of foo of something. So it's pretty easy to spot them if you're looking for them. So let's see another example. And we have this function that computes a lame nickname, like my own. And we have 3 functions to perform this incredible task. And these functions are getting a user, getting an age, getting a nickname. And I would like you to pay attention to the return types. So the first return type is our favorite type today. So it's future of option of something, of user. And the other 2, they cousins of that type, but they're not quite the same, right? So the future of int and option of string, they're both missing a piece. So if you try to compose them together naively, you just do this, and you run into troubles. So what's happening here? It's happening, the first one is fine. The first one is future of option. It is exactly what the apply method, which is the syntactic sugar is provided here, expects. So option T can construct an option T out of a future of option. The other 2 don't work. And this is why monad transformers for some things suck really bad. Because now you need to manually fit all those types in the stack that you have, which is future and option. And you need to do stuff. This is fitting the types. You need to do stuff like this. You need to do option T lift of F, which is an operation that takes a future of something and can transform into an option of future, option T of future of something. And then from option, it works from the option. If you don't have the future, you need to call the operation. So basing on the specific type you have, you need to manually go and try to fix the type into the desired data type, which is option T in the end. So this is where monad transformers start getting bad. So the scope of this talk is to make you realize where they're useful and where they're not. And if you have a lot of this lifting and stuff, you're essentially losing track of what was the original goal, which is making the code more terse and readable. So if you have a lot of this, it's not. So keep that in mind. So let's go for our final example, which is updating a user and on a database. So suppose you have this business operation that is checking whether a user exists, then checking it can be updated out of some logic, and then updated on the database. So you may be tempted to do something like this with the types. So you have a future of optional user for the checking that the user exists. You take a string, you take the user out. Maybe it's not, it's there, maybe it's not. Then you check it can be updated. Again, that's an asynchronous operation because maybe you need to hit the network to get information. And then you update the user on the database, which is, again, asynchronous. So you run into problems pretty quickly because you end up with code that looks like this. And, well, what is this code doing, right? If you remember the examples from Harry's talk this morning, where the play controller example, it looks pretty much like that. There's a lot of nesting. There's a lot of things going on. There's a lot of future of none. What is it? You need to go and backtrack where that curly brace is open and see why is there. And if you want to go with more detailed errors, so as we've seen in today's talk, if you want to be more precise, you may switch from option of something to something that gives you more information of why something has failed, which is either with a custom error, like my error. So if you want to do something like this, you end up with code that looks like this, which is terrible to me, and good luck maintaining this. So future of either or something, right? That's our type. So if you know where I'm going, is something like this, right? Of course, there must exist a transformer that does that. And in this case, we're looking for either t. You see the pattern here again? Either has two type parameters. We're just adding another one, and we're just removing the wrapping, so it's linear. So you have either t with three parameters, the wrapper, the a, and b. Don't take the wrapper too seriously, because that falls short very quickly if you're working with different data types that are not containers. But for the sake of the talk, it's fine. So how about we do something smarter with either t? Let's define some types. So we have a myError class, as it's always a good idea to have an error class that we use throughout all the application, or in some part of our application. Then we define a couple of aliases, and the final alias is the one interesting. We have this future result of A, which is essentially another t where we define that we're definitely going to use future, we're definitely going to use myError, and the only thing we don't know about is this A. Okay? So with that in mind, we define some helpers to construct types of future of results. Not advocating this is a good idea, but it makes the code slightly more readable. And then we can do something that helps in keeping the business logic more consistent, which is changing the return types of all the functions involved to this type. So we're moving the price of working with heterogeneous types when we're composing them together to the leaves, essentially. So we're paying a price. We're paying a price for changing this here. This gets a little bit more complicated to the single functions. So now what we're doing is to build a future of result instead of a future of option of user directly. But I would argue that it's not that much of a trouble. You just need to return, in this case, an either. And with these as right, as left, they come from cats, from syntax, or you just build them by hand. And then you do the same thing with the other methods. And then you can just compose them like this. So again, I think this is OK for this case. I think this is what we're looking for. You need to always pay attention to the fact that you didn't magically make some code disappear and be better. You just moved the burden of working with different heterogeneous types to the leaves, in this case, which I would argue is good, because when you're composing things, you can get exponential, essentially, complexity out of the composition of many, many things. And instead here, you pay linearly on every operation that you're implementing. So if you have a piece of code, a specific subdomain of your code where you're working with similar types, just sometimes they're a little bit off, like future of option of something, future of something, stuff like that, you may think of using this strategy. So this strategy consists in just use the same type for everything, so things become more composable. And you gain a lot when you're composing them together. So this is the trade-off that you need to keep in mind if you try to do something like this. So some personal tips for modern transformers. Don't stack more than two. If you're stacking more than two, you're essentially losing any benefit you may get out of those. So don't. Consider something else. You may running into very different problems than these are useful for, so don't. So this is an example. It's a tragic one. It's from M, interesting repo which tries to make modern transformers less confusing without getting to F, which is a different library. It's sort of in midway. And this is an example from the README, and this is option T of other T of task of string, whatever, the first line, essentially. And I would argue this is not readable, okay? There's a lot of lifting. This is what I was talking about before. There's a lot of lifting. There's a lot of heavy things going on, and you don't understand what's going on. So this is what happens if you try to stack a lot of types, because you never work with a precise type that you want, which is option of either of task, but you just working with different types and it's a mess. So tip number 2, this is very easy. Don't ever expose them to the user. It's just silly. You can just call value and get a regular Scala value out of it, and they're not standard in the library, so don't do that. I've seen them do it. It's not worth it. Plus, if you're considering doing this a lot, wrapping stuff is not cheap on allocations. So if you're doing that a lot and your application is bound by these kind of concerns, consider doing some benchmarking. Never take a blog post for granted, so don't do it. Benchmark your code, but keep in mind that this might be a suspect if you're running into performance problems with allocations. And fourth, which is I think the most valuable part, use them as a local optimization. Again, you can go home and take a for comprehension and make it nicer, and that's what I find valued in for using monotransformers. You have local things pieces of your code that just look a little bit the same, so you can just compose them together much more easily if you use a monotransformer. If you want to base your whole application on a stack of monotransformers, terrible idea, in my opinion. It doesn't scale. Whenever you need to add an extra layer, it just won't work. So the sense of this talk is to give you an impression of what they're useful for and what they're not, and I don't think using a complex stack of monotransformers is a good idea in general. Some other takeaways, well, they end with T. We've seen the pattern of f of g of x becoming g of t of f of x. They can be stacked indefinitely because whenever you stack 2, they become a monad, so you can go and go, but don't do it. And they're just one tool for working with stacked monads. So I'd like to conclude looking around and see what else there is. You may want to have a reader of a state, of a task, of something. So you want to compose many, many monads because they're practical and useful to work with, but you run into a problem of composition. So what else is there? So in order to solve the problem of having a clear business logic, free monads help. We've seen the talk today. Free monads allow you to separate structure from implementation, so the structure is always clean. But this doesn't save you the problems of working with then monad transformers or whatever in the implementation. So the interpreter of a free monad is where the nasty things happen. So by using a free monad, you just separated the structure from the implementation, but you didn't exactly solve the problem then implementing those. So if you want working with a complex stack with monad transformers, you still have the problem with free monads, but you're getting a very clear business logic, which is interesting. A more systematic approach to this is F. And I encourage you to go and check F if you want to work with a very complex stack of monads. F essentially works on the idea that a specific monad, you can squash a single monad, right? We've seen that before. If you have an F of A, you can squash them together, you can compose them together. It's easy if you work with a single monad. So the idea here is let's work with a single monad, which is F. F is a super powerful monad that you can essentially map every type that you have in your application to. So you can take option and reinterpret it in terms of F. You can take future and reinterpret it in terms of F. And you can do this for every type. And then you can just compose them together in a seamless way because you're just working with a single monad. And F has really nice properties. It tracks all the effects that are working in your stack. It doesn't require you to work with the whole stack all the time. You can just work with single pieces. So if you want to have just the semantic of asynchronicity, but and a writer because you're writing a log and you don't want to have optionality, you can do that. You can just have different pieces of your application working with different effects, and that works. So if your application requires a systematic approach, I would encourage you to try this. But if you want just a local optimization, monad transformers are really, really interesting. So you can apply them directly without changing the whole code base. So these are the compromises, guys. And thank you very much for listening. And if you have any question, I think we have a few minutes.
We have time for a couple of questions. Who goes first? Dun 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 dun. Dun 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 dun. Perhaps some introspection.
Some introspection. Asking myself.
Yes.
Was it a good idea to stack 3 monads? No.
Coming. Ah, wrong side. There we go. Are there any approaches to reducing boilerplate using macros or something in this case, like they have with free monads, where they have libraries generating stuff for you?
I never experimented on this specific problem using macros, but macros have usually the problem of solving a very specific syntactic problem, and this is more of a structural problem. So there's a talk which is really interesting by Dave Gurnell about when the talk is specifically about when using shapeless, when using macros. But the takeaway is interesting: is whenever you have a structural problem, you typically don't want to use a macro. Macro are very good for syntactical problems. You want to generate some code, you want to generate maybe a type class instance or something like that. But I wouldn't use it for solving these kind of problems because they can get unmaintainable and unpredictable very soon, and you risk to be very specific and that you don't have a general solution for your architecture. But I would like to see an approach, but I don't have any in mind.